You are listening to Climate Now. I'm James Lawler. Before we get started today, I'd like to invite everyone to subscribe to the Climate Now newsletter, which you can do at climatenow.com. Subscribers to our newsletter are the first to receive new episodes of the podcast, as well as deep dive articles in our Systems Thinking series, where we pull in all of the information that we've been gathering from our experts to give you a comprehensive overview of key topics related to the energy transition, such as decarbonizing road transportation and the energy efficiency resource. Creating industrial products like steel, concrete, and plastics require energy-intensive processes. Traditionally, producing that energy has involved burning fossil fuels, and a lot of them. Because of this, industrial emissions have been considered a hard-to-abate sector. But what are the opportunities to reduce industrial emissions, and what is being done today? We're pleased to be joined today by Dr. Rebecca Dell for a conversation on decarbonizing the industrial sector. Dr. Dell is the Industry Program Director at ClimateWorks Foundation. She also worked with the U.S. Department of Energy during the Obama administration, where she coordinated implementation of the Climate Action Plan. She has a PhD in climate science from MIT. Dr. Dell, thanks so much for joining us today.
Thanks so much for inviting me.
So tell us first about your background. How did you get to where you are today in your career? What led you here?
Yeah, people come to environmental work from a lot of different directions. I did not expect to end up here. I went into climate science because I really liked physics, and I thought that the physics problems of the ocean and atmosphere sounded interesting. But as you might imagine, being a climate scientist in our current moment is something of a radicalizing experience. And I spent almost 10 years between my PhD and working as a scientist. Slowly over that time, I realized that the thing that was holding back our action on climate change was not the quality of the science. And so I might be able to have a bigger impact on what was clearly the most important problem of my generation by getting involved in government and public policy. So that's when I went to work for the U.S. Department of Energy. I was there for 3 or 4 years and then left at the end of the Obama administration. And since then, I've been working for various NGOs and foundations in the climate space. And I ended up working on industry.
What was it like at the DOE? What was your role there, and what kind of work did you get into there?
Yeah, I found DOE to be a really exciting place to work. I was in the policy office, and this was a time of an enormous amount of interest from the secretary and even from President Obama in trying to figure out what can we do to move further faster on climate change. When I left the government, I took some time to kind of take a step back and survey the landscape. The big question I was trying to answer was, what are we not doing? What is the missing piece here? And I realized that if you look globally, the industrial sector is responsible for 1/4 of greenhouse gas emissions. If you add in the greenhouse gas emissions from generating all the electricity that's being consumed by industrial facilities, that goes from 1/4 up to comfortably more than 1/3, or uncomfortably more than 1/3 of all greenhouse gas emissions. So this is just a huge chunk. This is like one of our top tier climate problems is what do we do about the industrial sector? At the time that I was kind of going through this process back in 2017, I was looking around and there just were so few people in this space. Hardly any money, hardly any policy ideas, hardly any corporate initiatives. There was just nothing happening. And so I was like, okay, that looks like a place where I can really make a difference.
So what brought you to ClimateWorks, and what is ClimateWorks where you are today?
We're a grant-making organization that is exclusively focused on climate change. My particular focus, obviously, is in the industrial sector, which covers manufacturing, construction, mining, waste processing. Basically, when we talk about industry in the climate context, we're talking about stuff and not energy, the physical material of the economy. That's a lot of stuff. There are a lot of different activities and whole, sectors of the economy that are involved in making stuff or moving stuff around. But there's actually a very short list of activities that are responsible for most of the greenhouse gas emissions. And those are making the basic materials that we make other things out of. Things like steel, cement and concrete, fertilizer, plastic, the kind of basic materials that everything else is made out of. That's what's going to drive those greenhouse gas emissions. So I said about a quarter of greenhouse gas emissions are directly emitted by the industrial sector. 2/3 of that come from the industries I just listed.
Of the three that you mentioned, of sort of the three big contributors to industrial emissions, and again, you mentioned petrochemicals, concrete and cement and steel. Maybe we start with petrochemicals. What are the emissions from the petrochemical industry? How do they break down? What does that sector look like broadly?
So if you look at the total life cycle emissions of the petrochemical industry, we're talking about more than 3 billion tons of CO2 equivalent emissions per year from that sector. To give you kind of a frame of comparison, the total greenhouse gas emissions from the entire US economy are like 5.5 billion tons. It's a huge amount. It's half of the emissions of the entire US economy for this one sector. Most of those emissions are in the form of CO2, but also there's a large amount of emissions that come out as methane and as other non-CO2 greenhouse gases. Of that more than 3 billion tons, we're talking about probably 2/3 of it, so about 2 billion tons, come in the production of the chemicals, and then the 1/3 comes in the use or disposal of the chemicals.
So I wanted to sort of clarify something with you, and you could maybe shed some light on this. Our understanding is that plastics are created through hydrocarbon byproducts from fossil fuel consumption for energy. So one of the things we've been wondering is, do you see the plastics industry changing as a result of a move toward more renewable energy sources, in that there won't be necessarily that same flow of hydrocarbon byproduct from the production of fossil fuels for energy?
Yeah, that's a great question. And I think this is actually an area that I think is really kind of understudied and that might have big implications for the way that these industries evolve in the future. Because for the whole history of the petrochemical industry, it has kind of developed in tandem with the motor fuels and refining industries. And so most petrochemical facilities you'll find adjacent to refining facilities, and they're exchanging products and byproducts all the time. That being said, that's a relationship that is common and widespread in today's industry, but there's no necessary relationship there. So if you look around the world, there are giant chemical facilities spread all over the world. And what they use as their primary feedstock and primary energy source just depends on what's locally available. So in the United States, our chemical industry is very, very heavily dependent on methane and what are called natural gas liquids. And those are not refining byproducts. Those are things that sort of raw materials directly from the ground into the chemical facility. And we do that because those things are widely and cheaply available in the United States because of our, natural resources and the choices that we've made about drilling for those natural resources. In Europe, they don't have the same natural resources, so their chemical industry is very dependent on refinery byproducts, particularly naphtha. So there's crude oil extracted products, but things that typically come to them after the motor fuels have been taken out. In China, they have relatively modest domestic resources of both gas and petroleum. And so they do a lot of their chemical synthesis just starting from coal. They go from coal to chemicals, which is much more greenhouse gas intensive, but that's the natural resource that they have. And so that's the way they prefer to do it. So just because the refineries go away or the demand for motor fuel goes away, we should not expect that the chemical industry will somehow go away. Quite the opposite.
To what degree is recycled materials as a feedstock to the petrochemical industry currently developed?
The framework that I tend to use to think about this is when we're making petrochemicals, you need two things. You need both energy and you need feedstocks. And because in the feedstock, particularly in the case of plastic, the products themselves are made out of carbon. So you need carbon atoms from somewhere, and that's your feedstock. Today, we use fossil fuels for both the energy and the feedstock. And when we talk about decarbonization, people have a lot of ideas for both clean feedstocks and clean energy. And actually, most of the solutions that you'll find only are trying to solve one of those two problems. It's very unusual to find an approach that's trying to solve both. And so recycling is probably our best avenue, at least from a technical perspective, for clean feedstocks. Because you say, okay, we already have this mass of plastic in the world, and that has all the carbon atoms we need, and they're already in a similar chemical form to the outputs that we want because they're already plastic. We should be able to process that relatively easily and cheaply into new chemical products. Sure, in theory. In practice, we do a very terrible job of doing this. Just yesterday, a new report came out from the group Beyond Plastics, where they found that the United States Environmental Protection Agency, the EPA, estimates that between 8 and 9% of plastic in the United States is recycled. That's not an inspiring number. That between 92 and 93% of plastic at the end of its life is not recycled. And this report that just came out yesterday found that actually the EPA overestimated because they were using old numbers and old methodologies, and our rate of recycling in the United States is actually going down, not up. So the real number is somewhere between 5 and 6%. Mm-hmm. So, there's a really strong technical argument there, but as a matter of social and economic systems, we have not been able to make it happen so far.
Why is that? I mean, to your point earlier, we should know a way to process plastic, which is already near to the final form as the things we want to make from it. It potentially could even be easier than spending so much energy to drill these other materials. So why are we so bad at this? Why is it not more of a widely used feedstock in the first place?
There's a lot of reasons. The proximate reason is that the waste stream of plastic that we generate is very low value. So if you just look at kind of what is in a recycling bin and what ends up getting recycled, it is a mixture of lots of different types of plastic, of products that include plastic and other materials that are laminated together in ways that are very hard to separate. It includes trash and other things. And with the systems that we have in place today, trying to separate out the valuable material and recycle it, that separation process is more expensive than just drilling for more oil or more gas. So you say, okay, why is that? Why are our waste streams so low value? There's a lot of reasons, but one of them, I think a really important one, is that the people who manufacture and market the products have no responsibility whatsoever for what happens to those products at the end of their life. In a rational system, you might say, okay, every drinks bottle in the entire country should be made out of the same plastic. And you should just use the same formulation for every single bottle. And then when you collect the bottles, it's very easy to separate the bottles from the not bottles. And then you'll just have a pure waste stream of one type of plastic. But for any individual manufacturer, there's no rule you have to follow. So just make it out of whatever's convenient to you. So the products are designed in a way that makes them very hard to recycle.
You mentioned I think this was in a tweet you wrote, is the chemical industry is responsible for 8% of U.S. energy consumption. That industry makes plastics, fertilizer, and other essential products and has lots of cool technologies, but no clear climate vision. What are the different opportunities that are most likely to reduce chemical industry's emissions?
Yeah, I stand by that assessment. While the chemical industry, there's lots of interesting things happening, I don't think anybody has sort of a clear line of sight to what a climate-safe chemical industry is going to look like. There's a lot of open questions there. But I find it helpful, as I said, to use the framework of clean feedstocks and clean energy. So when we talk about clean feedstocks, we talked about recycling already. Other options include things like getting your carbon from biomass. That's certainly an option, but you pretty quickly start running into constraints on how much biomass you can actually source sustainably. That might be an important solution for part of the problem, but that's not going to be the broad stroke solution. There's also a set of people and companies who are increasingly thinking about, is there a way that we can just get the carbon out of the CO2 that's already in the atmosphere? So turn CO2 into chemicals. You can do that. It requires an extraordinary amount of energy. But I think there are some interesting startup companies and that kind of thing that are trying to commercialize CO2 to chemicals. But my rough back of the envelope calculation is that if the whole chemical industry today used CO2 and electricity to get its carbon instead of what it's currently doing, the amount of electricity that would be required would be basically 50% of all the electricity that we have on Earth. We could do it, but like, whoa, that's a lot of clean electricity we're going to require. And then on the clean energy side, we can always use clean electricity, and we should. And then I think we should also take really seriously options to be more material efficient. Everybody knows that you should be energy efficient, don't waste energy. But I think we're still, as a society, in a very early stage of our conversation about material efficiency. Can we deliver the same products and services, the same level of comfort to people, but just use fewer materials to do it?
I think that's such an interesting point. Oftentimes this conversation is localized around megawatts and around how much energy, how much this, but really what we should be asking is, the services, that's what we're trying to solve for. We're trying to solve for the results of this energy, not the quantity of energy itself. And that's where we often miss, I think, in this.
Absolutely. Things like we were talking about recycling. So if we can use secondary materials instead of new materials, that's great. But also these material industries, their products are very inexpensive. The cost of the actual plastic resin that is in your typical bottle of water that you might have bought for $1 or $2 is like 0.2 pennies. When you're selling a product for 1,000 times more than the cost of the materials that it contains, there's not a strong incentive for you to use those materials efficiently. and usually we don't.
Really interesting. So I want to move to the second industry that we want to talk about with you, which is the cement and concrete industry. So I wonder if you could first give us an overview. How is concrete produced? What's producing the CO2? What part of the process?
Yeah, this is your classic example of the effects of scale. Concrete has three main ingredients. It has sand and small rocks, which we call aggregates, water, and cement. And cement is basically the glue that holds the sand and small rocks together. And this gives you a material that has some really very, very convenient properties. Why do we love concrete so much? Because it's a rock that you can pour. We like rocks. They're very strong. They can hold up things. But actually carving rocks is very hard. With concrete, you just pour it and then it turns into a rock. And so it's very, very easy to make it. It's cheap and it's easy to make it in any shape that you want and in any location that you want to move it around. It's so much better than masonry, which is just rocks. So we use it in fantastic quantities. Total global concrete consumption is somewhere between 30 and 35 billion tons per year, which it's an insane number. And basically what that corresponds to is about 10,000 pounds of concrete per human per year for every single human being on the entire planet. It's so much. And the greenhouse gases emissions are really driven by the cement. So it's not that the cement is so greenhouse gas intensive itself, but it's just that we make billions of tons of it. And so We talked about the plastics and chemical industry, the petrochemical industry being responsible for about 3 billion tons of CO2 per year. The cement industry, it's like 4 billion tons.
Wow. You mentioned in a recent op-ed for the New York Times that using low CO2 concrete could reduce concrete CO2 emissions by 20% or more. This includes reducing the cement in concrete, replacing it with additives like CO2 or fly ash, which is a byproduct of the fossil fuel combustion process. We've heard of a couple of companies, that sell CO2 to concrete makers. Cemex has created low and net zero carbon concrete and cement by recycling concrete and reforesting quarries and also using alternative additives. There are other companies. Can you talk about sort of what these various companies are doing and pros and cons of their methodologies?
Sure. So basically, the main ingredient in traditional cements is something called clinker. And making the clinker is what generates the overwhelming majority of the greenhouse gas emissions. And so in order to get to zero, in order to actually zero out our emissions from the cement industry, we are going to have to figure out ways to make clinker without emitting greenhouse gases. That's eventually we're going to have to get there. However, before we do that, we have enormous opportunities to make both low clinker cements, so just use other ingredients that have lower greenhouse gas intensity than clinker to make our cement, and then also to make low cement concretes. And those are things that in many cases, there aren't any technical barriers. There are techniques for doing this that have already been used in many applications for decades in different countries around the world. We know that they work, but they're just not widely and certainly not universally adopted. And often you can save money by doing those things because the clinker is not just the most CO2 intensive, it's also the most energy intensive ingredient. You mentioned, for example, fly ash, which is a byproduct of coal combustion, so burning coal. You can blend that into your cement and replace a significant portion of your clinker and reduce CO2 emissions that way. There are other of these types of additives that are widely available. Some of them are industrial byproducts, some of them are natural materials, and some of them are processed materials, but they're materials whose processing doesn't emit the same kind of greenhouse gases. In my opinion, one of the most interesting and exciting opportunities here is LC3, which stands for limestone and calcined clay cement. This is a cement that has only 50% clinker, where traditional cement is 95% clinker. And the other 50% is made up with limestone and calcined clay. So these are other types of rocks that are widely available and that require much less processing than traditional cement, and so emit much less greenhouse gas than traditional cement. And if you blend them together in the right way, you basically get a drop-in substitute for our traditional cement. You can use it in exactly the same way, but since you've reduced the amount of clinker by almost half, you reduce the total greenhouse gas emissions by 30 to 40%.
So why is this not more widely used?
I mean, the short answer is that there's no incentive in most places.
Is it more expensive?
Nope, it's not. In most places, it will be cheaper.
Isn't that an incentive if it's cheaper?
Well, for private construction, for just people building buildings in the United States, the cost of the cement is less than 0.5% of the cost of a construction project on average. And so if somebody comes to you and says, hey, I've got a great idea, I can get your cement bill from 0.4% of your budget down to 0.3% of your budget, you might be like, I think I might get more payback if I focused my attention elsewhere. It's hard to get people to use a material efficiently when it's that cheap. The first customers are in emerging economies where they are building new cement kilns and building new cement facilities. And so, their attitude is like, well, why don't we just start with the cheaper thing? So there are a couple of factories currently under construction, one in Colombia and the other one I think is in India, But I have a lot of optimism that this is something that could be taken up very widely.
So what gives you that optimism? I mean, you described a picture that sounded pretty bleak on the face of it, in that we consume and we're using a huge quantity of concrete annually. And the incentive to make any kind of process change, which would reduce the emissions profile of the materials and sort of the process itself, is almost non-existent.
Yeah, well, so I think that the fact that it is available and cheaper, that is helpful. I don't think that's enough to get widespread adoption tomorrow. But I think in order, with LC3 or with any of the options that we have, moving further faster is going to require policy and market interventions. So one of the things that I spend a lot of my time working on is a set of policies that we call Buy Clean, so we were previously talking about private construction, but actually an enormous amount of cement and concrete goes into public construction. In the United States, it's almost half of all cement goes into construction projects that are paid for with taxpayer dollars. So one really great way for us to get started in moving down the emissions curve here is for the government to say, if you want us to buy your cement, it has to be produced in a responsible way.
Are there any other opportunities to reduce emissions from the concrete industry?
The big one also is, again, material efficiency. We are just astonishingly wasteful in the way that we use cement and concrete. And this is not something that is somehow specific to high-income countries. We think that actually the use efficiency of cement is probably lower in low-income countries than it is in high-income countries.
What does a more efficient use of concrete look like?
So, people have done studies where they look at buildings and infrastructure and things like that, and they say how much concrete would be required to comply, like how much structural material do you need to make sure that not just will the structure stand up, but you have all of the appropriate safety margins and you are fully in compliance with all of the appropriate building codes. How much do you actually need in terms of structural material? And they frequently find that there's between 50 and 100% more structural material than is required to comply with our extremely safety protective building codes. They just use twice as much concrete as they need.
Why is that?
It all goes back to how cheap concrete is. So, for example, let's say you have a certain size that you need for the foundation of a structural pillar in a building. And so the engineer for the building will specify this is how big the foundation needs to be. Then the contractor shows up and the contractor has the option of digging a very precise hole that's exactly to the specifications of the engineer and probably building a mold that would go down into that hole that you would pour the concrete into to get exactly the thing. Or option B, the contractor can just dig a big hole that is bigger than what the engineer specified and just fill the whole hole with concrete. Option B requires a lot less labor, but a lot more concrete. But labor is more expensive than concrete, so they often go with option B. And so, in my opinion at least, we are going to have much more targeted requirements in addition to carbon pricing if we decide to do that.
Interesting. And you're developing policy recommendations now on what that targeted price structure would look like?
So we already talked about one example, which is Buy Clean regulations. And so that's a situation where it's not really a price mechanism. What's happening is that the biggest customer, the government, is saying, we simply won't buy your product unless you meet our standards. And it has nothing to do with the price. It's just, you're just not eligible unless you meet the standards.
And where are you with the development of that?
We have several U.S. states have adopted Buy Clean laws. This is our first year with compliance obligations in California, which is the first state to have this law. That will start this summer. And then President Biden also instructed the federal government to start developing these policies back in December. And part of the federal government, what's called the General Services Administration, so this is the part of the federal government that is responsible for overseeing the federal real estate portfolio, so all the buildings that the federal government owns, which is that's a lot of buildings. So they have just recently announced their first proposed standards for low GHG building materials for federal buildings.
That's great. So I'd love to hit our last sector here, which is steel. Steel emits the most greenhouse gases of the industrial sector. Why is that?
I mean, it has a great combination of high CO2 intensity and high volume of production. So, it's you're multiplying two large numbers together. So it's worth just pausing for a minute to acknowledge that every steel mill on Earth makes more CO2 than steel. In terms of the total mass of its products, it's a CO2 facility that also makes steel.
That's an incredible frame.
When we make aluminum, that number is not 2 tons of CO2 per ton of steel. It's 18 tons of CO2 per ton of aluminum. But we use a lot less aluminum, and so the total global emissions of the aluminum industry are very small compared to the total global emissions of the steel industry. On some level, why is steel the highest emitting industry? Because steel is fantastic. Steel is so great. I mean, think about it. It's strong, it's stiff, it's formable, it's durable. It has a wide variety of valuable thermal and electrical properties. It's fantastic. We love it. And so we use it for everything.
Why is it so emissions intensive in terms of the process of making steel?
Steel is almost all iron by weight. And iron atoms really, really like to bond with oxygen atoms. And so you have to run that chemical reaction backward in order to get back to metal. And that requires a lot of energy. And the way that we supply that energy in almost all cases is by burning coal. And so there you go, 4 billion tons a year of CO2.
So what are the opportunities then to reduce the greenhouse gas emissions in the life cycle of steel?
There's a bunch of things we can do. We've already talked about material efficiency in the context of other industries. We can and should you do that in steel. We should also recognize, however, steel is already the most recycled material on the planet. We recycle 85% of steel. We actually do a really good job of collecting steel and reusing it at the end of its life. That's a real option. We should pursue it. We should also understand, though, that it's not necessarily the low-hanging fruit. If you want to make new steel, then you still have to do that chemical reaction where you pull the oxygen and the iron atoms apart. There's a startup company called Boston Metal that is basically trying to use electricity directly to do this. And so basically you take a bunch of this iron oxide, you get it hot enough to melt it, and then you just put an enormous electric field across it. And the electric field is so strong that it just directly pulls apart the iron and the oxygen. So that's one option. That might be a really good option, but it's what we call a pre-commercial technology. That's a technology that's still in development. Another option is that instead of using coal, you could use hydrogen. The most kind of prominent example of this is a project that's being sponsored by the European Union and the Swedish government called Hybrit, which is it's in Sweden, where they are designing and building a new kind of furnace that will be fed by hydrogen instead of by coal. And so you imagine you're pulling off these oxygen atoms, you're giving them a new place to hang out. If coal is carbon, if the oxygen atoms are heading toward the coal, you're going to get CO2. If the oxygen atoms are heading toward hydrogen, you're going to get H2O, which is a much less obnoxious gas to have in our atmosphere because it's water.
Right.
In case that wasn't obvious.
ArcelorMittal has announced they're using this electric arc furnace. What does that mean exactly?
Sure. So an electric arc furnace is a thing that we use already in the steel recycling industry. So an electric arc furnace is a purely electric technology, and it's something that we use to melt the steel. Basically, what happens is the current steelmaking technology, which is called a blast furnace, is you just put in the iron ore and the coal, and you get melted steel out. The alternative technologies, often either with scrap or with the hydrogen reduction or other technologies, you end up, when they're finished with their processing, you get solid iron. And so you need to melt it so that you can control its composition and form it into products. So the electric arc furnace is kind of like all of these technologies are funneled into the electric arc furnace, which is kind of a core processing stage for your steel for a lot of different potential iron making routes. Companies like ArcelorMittal, they're very traditional blast furnace companies. And so for them, it's a really important step toward the next generation of steelmaking to say that we're moving away from the traditional blast furnace. We're opening up the possibilities for all of these different iron making routes by investing in both the physical assets and the company expertise for the electric arc furnace.
Of these different steelmaking technologies, what do you think is most promising?
The way that I usually think about it is that the hydrogen route, that's the one that's closest to being ready to go. So I think, 5 years from now, we are going to have hydrogen steel mills that are producing commercial quantities of hydrogen reduced steel. And people are going to be out there making them into cars and products and everything. So that's actually pretty close to being ready to go. However, it requires more energy than the electrolysis Boston Metal type route. And these are very, very energy intensive processes. The steel industry globally uses 5% of all energy that's consumed by humans on Earth. So if we can get the electrolysis route working soon, that's going to be even more attractive because you can save so much money on your energy. So I think it's probably going to end up being a combination of those two, supported by better, higher quality recycling with more material efficiency.
That was Dr. Rebecca Dell from ClimateWorks Foundation talking to us about innovations and opportunities to decarbonize the three biggest emitters of the industrial sector: chemicals, concrete, and steel. To listen to other episodes, watch our videos, or read our articles, visit climatenow.com. To get in touch with us, please email us at contact@climatenow.com. We hope you'll join us for our next conversation.